Last chapter we seen S block element. That new chapter is P block elements. The P block elements, the last electrons enter the outermost p orbital. So as we know that the number of p orbital is 3, and therefore the maximum number of electrons that can be accommodated in a set of p orbital is 6. Okay, we can accommodate 6 electrons. That is, the consequently are 6 groups are there. That is, the p block elements having, that is, group 13 to group 18. Group 13 to group 18. So there are 6 groups are there. Here the general valence cell electronic configuration is ns2 np 1 to 6. In only in the case of except that helium having ns2. The rest of the elements they end with p, that is np 1 to 6. Okay. Here this general electronic configuration and the oxidation state of the p block element is, first I will tell you what are the elements are present in the p block element. So group 13, that group 13 is boron. Group 14 is carbon. Group 15 is nitrogen. Group 16 is oxygen. Group 17 is fluorine. Then the group 18 is helium. So these are the group members. That is the here this contains some element, that is boron family, carbon family, nitrogen family, oxygen family, that halogens family, and that noble gases. So like this. Here the general electronic configuration of that group 13 element is ns2 np1. Here carbon is ns2 np2. That is the outer electronic configuration. That is the general electronic configuration, or you can tell that is outer electronic or valence cell electronic configuration. Then nitrogen is ns2 np3, oxygen ns2 np4, fluorine ns2 np5, helium ns2 only. Generally then helium 1s2, that is ns2 for helium is 1s2. The rest of the elements, that group member is ns2 np6. Okay. Here this is the group first member. Okay, I am telling the first member. The group oxidation state of this element is boron having +3 oxidation state, carbon having the +4 oxidation state, nitrogen having +5 oxidation state, oxygen +6. Then that is the group oxidation state. I am telling the group oxidation state, and there is fluorine is +7, and that the noble gases +8. Here the other oxidation state, that is the possible oxidation state for boron is +1, nitrogen carbon +2, -4, then nitrogen is +3 and -3, then oxygen is +4, +2, -2, then that in halogens having +1, +5, +3, +5, +7 already is there, then -1. Then this noble gases having +6, +4 and +2 oxidation state. This is the other oxidation state, that is the possible oxidation state. Now we will discuss in this year you are going to learn the group 13 and the group 14 elements only. The group 15 to group 18 elements you are going to learn in higher secondary second year. Okay, in this year you are going to learn the group 13 and the group 14 elements only. Now we will see the group 13 elements. Group 13 elements, that is we are going to discuss here, the boron family. Here the boron is a typical non-metal. Aluminum that contains the group boron family, that aluminum is a metal but shows many chemical similarities to boron and gallium. Indium and thallium are almost exclusively metallic in character. Here, the boron is a fairly rare element, mainly occurs as orthoboric acid. That is, the formula is H3BO3. Orthoboric acid. This is the borax Na2B4O7.10H24 and kernite. That is the borax form. Here, the abundance of boron in earth crust is less than 0.0001 percentage by mass. There are two isotopic form of boron, that is, the boron is 10 as 19% and the boron 11 as 81%. This is 19% and this is the 81%. There is a two isotopic form. Then aluminum is the most abundant metal and the third most abundant element in the earth crust, that is 8.3% by mass, the aluminum. Okay, then after oxygen is 45.5, silicon is 27.7%, bauxite and cryolite, like this, the important minerals of the aluminum. Okay, here the atomic and physical and chemical properties of these elements, that is electronic configuration, atomic radii, ionization enthalpy, electronegativity. Then the physical properties, chemical properties we are going to see here. First we will see the electronic configuration. Electronic configuration of the group 13 element. See, here the group 13 element, the outer electrons, the electronic ns2 np1, already we seen, that is ns2 np. A close look at the electronic configuration suggests that while boron and aluminum have noble gas core, gallium and indium have noble gas plus 10d electron, and thallium has noble gas plus 14f electron plus 10d electron core. So the electronic structure of these elements are more complex than for the first two groups, like group 1 and the group 2, that is the alkali and alkaline earth metal. Here next is the atomic radii. The atomic radii, that is moving down the group, for each successive member one extra cell of electron is added, and therefore atomic radius is expected to increases. So however the deviation can be seen, that is the atomic radius of gallium is less than that of the aluminum. Then this can be understood from the variation in the inner core of the electronic configuration. Then the presence of additional of 10d electrons offer only poor screening effect. Already we seen the screening effect for the outer electron from the increased nuclear charge on the gallium. Similarly, the atomic radius of gallium is 135 picometers less than that of the aluminum, that is 143 picometer. Then the ionization enthalpy. The ionization enthalpy values is expected from the general terms do not decrease smoothly down the group. The decrease from boron to aluminum, so they are decreased, that is associated with increase in size. The observed discontinuity in the ionization enthalpy values between aluminum and gallium, between indium and thallium are due to the inability of the d orbital from f electrons, which have the low screening effect, to compensate the increase in the nuclear charge. So that the ionization enthalpies are expected is usually that ionization enthalpy 1 is less than ionization enthalpy 2 is less than ionization enthalpy 3. Okay, so the sum of first 3 ionization enthalpy for each element is very high. So effect of this will be apparent when you study this the chemical properties. Then the next is the electronegativity. The electronegativity, that is the down the groove, electronegativity usually decreases from boron to aluminum and then increases increases from the marginally due to the presence there is the discrepancy of the atomic size of the element. Okay, then physical properties. The physical properties of group 13 element. Boron is a non-metallic nature. It is extremely hard and black color solid. It is exists in many allotrophic form. Then due to very strong crystalline lattice, boron has unusually high melting point. So rest of the members are soft metal with low melting point and high electrical conductivity. That is, it's worthwhile to note that the gallium with unusually low melting point, the gallium is melting point is 303 Kelvin. So the melting point is gallium is 303 Kelvin melting point for that could exist in the liquid state during the summer. Okay, so its high boiling point makes it the useful material for the measuring high temperature, so that the density of the elements increases down the group from boron to thallium. Next, chemical properties. The chemical properties are the oxidation state and the trends in the chemical reactivity. Here, due to small size of boron, the sum of first 3 ionization enthalpies are very high. That you can see the table number 11.2. The physical properties are given in that group, that is boron from group 13 elements. Now here the first 3 ionization enthalpies are very high, so that this prevents it to form +3 ion and forces it to form only covalent compounds. So, but as we know, that is, we move from boron to aluminum. Yes, boron to aluminum. The sum of the first 3 ionization enthalpies of aluminum considerably decreases and therefore able to form Al3 plus ion only. So, in fact, the aluminum is a high electropositive metal. However, down the group, due to the poor sealing effect of intervening d and f orbitals, the increased effective nuclear charge holds ns electrons tightly. Okay, so and thereby the restricting their participation in bonding. So as a result, the only p orbital electron may be involved in the bonding. So in fact, the gallium, indium, and thallium both that is having +1 and +3 oxidation states are observed. That the relative stability is +1 oxidation state to predominant, whereas the +3 oxidation state high oxidizing character. So the compounds in +1 oxidation state, as expected from energy consideration, are more ionic than those in the +3 oxidation state. So in trivalent state, the number of electrons around the central atom in a molecule of the group, molecule of the compounds of these elements, like example boron trifluoride, will be only 6. That is, they are simply called electron deficient molecules. So the electron deficient molecule have tendency to accept a pair of electron to achieve stable electronic configuration, and thus the behavior as a Lewis acid. So the tendency to behave a Lewis acid decrease with increase in the size down the group. So suppose take the BCl3 boron trichloride easily accept a lone pair of electron from ammonia to form BCl3 dot NH3. See, look at this. So BCl3, this is a planar structure, react with ammonia. So what happens means to form a tetrahedral manner, that is B, Cl, Cl, Cl and NH3. So this is tetrahedral manner, this is planar. Okay. Usually they form BCl3 dot NH3. Here then AlCl3 achieves stability by forming a dimer form, that is Al aluminum chloride, AlCl3. So we can write it that AlCl3 like this. This is one form, and one more is there, that is the dimer form. We can write like this, AlCl. So here this chlorine and aluminum, the bond length is 221 picometer and this angle is 79 degree and this angle is 101 degree. Here this chlorine aluminum bond length is 206 picometer and this bond angle is 118 degree. So this is the tetrahedral manner. So in a trivalent state, most of the compounds being covalent are hydrolyzed in water. For example, the trichlorides on hydrolysis in water form tetrahedral, like metal OH4 times minus. So the species like hybridization state, the element metal is sp3 hybridization state. Then aluminum chloride is acidified aqueous solution form, octahedral, like Al H2O 6 times 3 plus. That is the 3 plus ion. So in this complex ion, the 3d orbitals of aluminum are involved and the hybridization state of aluminum is sp3 d2. So this octahedral state. The next is reactivity towards air. Now this we'll see the reactivity towards the air. Here the boron is unreactive in crystalline form. Aluminum forms a very thin oxide layer on the surface which protects the metal from further attack. Then the amorphous boron and aluminum metal on heating and air form boron oxide, that is boron trioxide and aluminum trioxide. So with dinitrogen at high temperature they form nitrate. So this is the reaction. Here the E indicates the element. You can write that boron or the aluminum. So to form, suppose if you write boron means react with oxygen B2O3, aluminum means Al2O3. Then reaction with the nitrogen same like this Bn, that is boron nitrogen, then like aluminum nitrogen. So this is the dinitrogen to high temperature forms nitrites. The nature of these oxides varies down the group. That is the boron trioxide is acidic and reacts with basic, that is the metallic. The basic oxide form the metal borates. Aluminum and gallium oxides are amphoteric and those of indium and thallium are basic in their properties. Next is the reactivity towards acid and alkalis. The boron does not react with acid and alkalis even at moderate temperature, but aluminum dissolves in mineral acid and aqueous alkalis and thus shows amphoteric character. So aluminum dissolve in dilute HCl and the liberation of the hydrogen gas. So when you aluminum react with the HCl to form AlCl3 like this, and the hydrogen gases evolve. However, the concentrated nitric acid renders aluminum passive by passing a protective oxide layer on the surface. So here look at this reaction. Aluminum react with base and the aqueous form to form the tetrahydroxoaluminate. This is a complex, and hydrogen gases evolve. Okay. Then reactivity towards the halogens. So these elements react with halogens to form the trihalide, except thallium iodide. Here, this reaction element indicates there's any element in that group 13 elements. X2 is a chlorine, either fluorine, chlorine, bromine, or iodine. You can use it. So it will form the trihalides. For example, boron react with 3 moles of chlorine to form 2BCl3. Like this, you can use it fluorine, iodine, whatever it is, okay, in that halogen. Next class we will discuss the next topic, that is anomalous properties of boron.